is big group. Wortman first of big group. Its first of big group. Wortman first of big group.
Pramodini, am I audible?
Yes, sir.
Okay. So, tomorrow, if you are Odia or non-Odia?
Odia, sir.
Odia. Kooti ghar tomorrow?
Chhatrapur.
Chhatrapur, Berhampur re.
ଆଜ୍ଞା
ଆଚ୍ଛା BSc କୋଉଠି କରିଥିଲ?
ସାର୍ ମୁଁ ଆକ୍ଚୁଆଲି 2013ରେ ମୁଁ ସିଟି ପରେ ପାଇଯାଇଥିଲି ଜବ୍ ତ ଇଗ୍ନୋରେ ହିଁ BSc ଟା କରିଥିଲି।
ଆଚ୍ଛା କୋଉଠି BSc ରେ ଅନର୍ସ କଣ ଥିଲା?
କେମିଷ୍ଟ୍ରି ସାର୍।
ଓକେ ତାପରେ ବର୍ତ୍ତମାନ ସ୍କୁଲରେ ପାଠ ପଢଉଛ?
ହଁ ସାର୍।
କୋଉ ସ୍କୁଲରେ ଅଛ?
ସାର୍ ଏପଟେ ଛତ୍ରପୁର ବ୍ଲକ ରେ ହିଁ ଅଛି। ପୂର୍ବରୁ ମୋ ବାପାଙ୍କ ପାଖରେ ଥିଲି ମୁଣ୍ଡମରେଇ ଧରାକୋଟ ବ୍ଲକ ରେ ଥିଲି।
ହୁଁ
ତାପରେ ମ୍ୟାରେଜ ପରେ ଏଇଠି 8 ବର୍ଷ ହେଇଗଲାଣି ଟ୍ରାନ୍ସଫର କରିକି ପଳେଇ ଆସିଛି। ଛତ୍ରପୁରରେ ହିଁ ଅଛି ସାର୍।
ଆଚ୍ଛା ଓକେ ଓକେ। ତମର ଅଲତର ପେପର ଯୋଉ କ୍ଲାସ ହୁଏ ଆଟେଣ୍ଡାନ୍ସ କେମିତି ରହେ ପିଲାଙ୍କର?
ସାର୍ ପୂର୍ବରୁ ତ ମୁଁ ଆକ୍ଚୁଆଲି ମୋ 18 ଆଉ 19 ଟା ମୋର ହେଇଯାଇଥିଲା ତ ମୁଁ ଆଉ କ୍ଲାସ୍ କରିନଥିଲି। ତା ପୂର୍ବରୁ ଯେତେ କ୍ଲାସ୍ କରିଛି ପିଲା ଥିଲେ ସାର୍ 20 ଏଭବ ଏମିତି ପିଲା ରହୁଥିଲେ। ଏବେ ମେ ବି କ୍ଲାସ କରିବେ ସାର୍ କାହିଁକି ନା ପୂର୍ବର କ୍ଲାସ ଗୁଡାକ ପିଲାମାନେ ପ୍ରାୟ ଏକ୍ଜାମ ଦେଇକି ପେପର ଦେଇକି ପାସ୍ କରିଦେଇଥିଲେ ତ ଆମେ
ହୁଁ
ବି ଜଏନ କରୁନଥିଲେ କଣ ମୁଁ କହିପାରିବିନି ରିଜନ ହେଇପାରେ। କିନ୍ତୁ ଏଇଟା ଏବେ
ତାପରେ ବି ତ ନୂଆ ପିଲା ଆଡମିସନ କରୁଛନ୍ତି ନା ପ୍ରତ୍ୟେକ ବର୍ଷ 2 ଥର ଆଡମିସନ ହଉଛି।
ହଁ ହଁ ସାର୍
ତ ପିଲା
ତ
ପାସ୍ କରିବେ ପୁଣି ନୂଆ ପିଲା ଆସିବେ।
ହଁ ହଁ ସାର୍।
ହୁଁ। ତ ପିଲା ତ ଆସିବା କଥା।
ସାର୍ ମୁଁ ଏବେ ଗ୍ରୁପରେ ଲେଖି ଦଉଛି ଜଏନ ହେଇଯିବେ।
ହଁ ଓକେ ଓକେ ଓକେ।
ମାନେ
ତ
ଯୋଉ
ତମର
ଗ୍ରୁପ
ତମର
ଅଛନ୍ତି
କୋଉ
ସେଇଠି ମୁଁ
କୋଉ
ଟିକେ
ପେପର ଆଚ୍ଛା କୋଉ ପେପରରେ ତମର କ୍ଲାସ ସରିଲାଣି?
ସାର୍ ଏବେ 16, 17, 18, 19 ଆମର ଯୋଉ ଇନଅର୍ଗାନିକ ପେପର ଟୁ ଅର୍ଗାନିକ ପେପର ଥିଲା ତା ସହିତ ଗ୍ରୀନ କେମିଷ୍ଟ୍ରି ଆଉ 18 ପେପର ଥିଲା ସେ ସବୁ କ୍ଲାସ ସରିଗଲାଣି ସାର୍। ଆଜିଠୁ ଆମର ଥାର୍ଡ ସେମିଷ୍ଟାର ଷ୍ଟାର୍ଟ ହଉଛି।
ଆଚ୍ଛା ଓକେ। ହଁ ବର୍ତ୍ତମାନ ମୁଁ ସ୍କ୍ରିନ୍ ଟା ସେୟାର କରୁଛି ତମକୁ ବୋଧେ ଭିଜିବଲ ହଉଥିବ।
ଆଜ୍ଞା।
So MCH-20 ର ତମର ଫାର୍ଷ୍ଟ ୟୁନିଟ୍ ଅଛି ଫଣ୍ଡାମେଣ୍ଟାଲ୍ସ ଅଫ ସ୍ପେକ୍ଟ୍ରୋସ୍କୋପି। ଏଟା ୟୁନିଟ୍ 1 MCH-20 ପେପର।
ଆଜ୍ଞା।
ଓକେ।
ସାର୍।
ସୋ ସ୍ପେକ୍ଟ୍ରୋସ୍କୋପି ତମେ ତ BSc ରେ ତ ନିଶ୍ଚୟ ପଢିଥିବ।
ଆଜ୍ଞା ସାର୍ ବହୁତ
କିନ୍ତୁ
ଦିନ ହେଇଗଲାଣି ନା ଏବେ ଟିକେ
ମନେ ନଥିବ ରାଇଟ ରାଇଟ। ସ୍ପେକ୍ଟ୍ରୋସ୍କୋପି ହଉଛି ଗୋଟେ ଆନାଲିଟିକାଲ ଟୁଲ ଯୋଉଥିରେ କି ଆମେ ଟେକ୍ନିକାଲି ଅର୍ଗାନିକ କମ୍ପାଉଣ୍ଡ ମାନଙ୍କର ବିଭିନ୍ନ ପ୍ରକାର ତାଙ୍କର ଇଣ୍ଟେନ୍ସିଟି ଷ୍ଟ୍ରେଚିଂ ଫ୍ରିକ୍ୱେନ୍ସି ୱେଭ ନମ୍ବର ଏସବୁ ଜିନିଷ ଟେକ୍ନିକାଲି ଆମର କଣ ହୁଏ ନା ଡିଟରମାଇନ କରାଯାଏ। ସୋ ଅଦର ପିଲାମାନେ ଜଏନ କଲେ ବୋଧେ।
ମୁଁ ଗ୍ରୁପରେ ମେସେଜ କରିଦେଇଥିଲି।
ହଁ କୁହନ୍ତୁ। So Adyasa, am I audible? Adyasa? One is Kailas.
Good evening, sir.
Good evening. So Adyasa, give your introduction, please.
Sir, actually, my name is Adyasharya Prabha Panda, and currently I'm doing uh, open MSc Chemistry, and already I appeared for two same exams, and this will be my third sem.
Okay, where are you from?
So basically, actually, I'm from Odisha, but currently I'm residing at Maharashtra.
Okay, so where you did your BSc degree?
Odisha only, sir, under Utkal University.
In which college?
Sorry, sir. Hello.
In which college?
FM College.
FM College, Baleswar. Okay, okay, okay. So thank you. Hope we will have a
Uh,
nice session. So then
thank you,
Kailash,
sir.
Kailash, am I audible, Kailash? Okay, so I think Kailash is left now. So we have, okay, so um, my screen is visible, students. Anyone, please respond. My screen is
Yes, sir.
visible.
Yes, sir.
Okay,
Sir,
okay,
yes.
thank you, thank you. So your MSc chemistry uh, distance learning, your second semester course code MCH-20 on behalf of IGNO Bhubaneswar, Regional Center Bhubaneswar. I welcome you all to this online platform, which is organized to uh, for the theory paper discussion of your MCS-20 and MCS-21. I will continue both the papers in 8 classes. Today is the first class, and so in this MCS-20, you have 6 units. So we have to cover the 6 units in 4 days. So I will. So it is. I will just discuss the important aspect of your spectroscopy and followed by the different type of spectroscopy. But in the paper MCS-20 is named as atomic and molecular spectroscopy. So this is all about your everything is related to your physical spectroscopy. The physical aspects like rotational vibration, as a rotational motion, vibrational motion, and the frequencies involved in this the different type of transitions made through rotation and vibration. So we have the first unit spectroscopy, and it is all about the fundamentals. So regarding the spectroscopy, we have the first part, that is EM radiation, which is also known as electromagnetic radiation. So it is associated with both electric and magnetic field. So in electromagnetic radiation, the electric and magnetic field are propagated perpendicularly. The two lines of forces are just perpendicular to each other, that they made 90 degrees with each other, and they can travel with the speed of light equal to the speed of light. That means it is 3 into 10 to the 8 meter per second. And the another characteristics of your electromagnetic radiation, it can propagate through vacuum also. That means it doesn't require any medium for its propagation. And we have different types of electromagnetic radiations, like in increasing order of frequency. The order is cosmic ray, gamma ray, X-ray, UV, ultraviolet, visible, UV visible, then it is infrared, IR, then microwave, radio wave. So radio wave has the maximum wavelength and minimum frequency, and this series or the sequence, which I have already stated, it is known as the electromagnetic spectrum. That is the ascending order of electromagnetic radiation in increasing order of wavelength is known as electromagnetic spectrum. Okay, so we have different units we may say, or parameters we may say, that involves the different measurement of a wave, because light is nothing but a characteristics of both particle character and wave character according to D. Broglie. So light also has a dual character, particle character and also a wave character. So in wave character, we have different mm, aspect of wave, that is wavelength, wave number, frequency, amplitude. Okay. So what is wavelength? The wavelength may be defined as, here it is written, just see here. It is the wavelength. It is represented by the symbol lambda, and wavelength is the distance between two consecutive crest or two consecutive drop is known as wavelength. That means the ଓଡ଼ିଆରେ କହିଲେ it is ମାନେ ଆମର ତରଙ୍ଗ ବା ଢେଉର ଦୁଇଟି କଣ ଅଛି, ପ୍ରଭାବ ଅଛି, ଗୋଟେ ହଉଛି ଜୁଆର, ଗୋଟେ ହଉଛି ଭଟ୍ଟା. So one is known as crest, another known as a drop. So the distance between two consecutive crest or two consecutive drop is known as wavelength. So as it is the length, so its units are meter, micrometer or nanometer. Then the word comes, that is wave number. What is wave number? Wave number is number of waves passing through unit distance per time is known as wave number. That means in an unit distance, how many number of waves are passed per time is known as wave number. And wave number is reciprocal of wavelength. So nu bar equal to 1 by lambda. So the unit becomes meter inverse or second inverse. Then we have the third parameter. It is the frequency of wave. What is frequency? The number of waves passing through a particular point. So through a point per time is known as frequency. So frequency, it is equal to velocity of light divided by wavelength. So its units are hertz or second inverse. So we have the next characteristics of electromagnetic radiation, that is the velocity. The velocity, we know that a radiation which is just wait. A radiation that has a measurable speed at a particular direction is known as velocity. So velocity, it is equal to c equal to v into lambda, which is equal to meter per second. Then we have the energy, E equal to hc by lambda, which is from your De Broglie equation, and its units is joule. And another parameter or characteristics of wave is there, which is known as amplitude. Amplitude is defined as the height of a crest or depth of a trough is known as amplitude. So these are all some characteristics of a wave, depending on its different units of measurements are there. So just see here, this is the electromagnetic spectrum. Here figure 1.2, it is electromagnetic spectrum, which is starting from the gamma ray, and the cosmic ray, it is not written here, but before gamma ray it is cosmic ray. So cosmic ray, gamma ray, X-ray, UV, visible, IR, microwave, radio waves, and long radio waves. So this is in increasing order of frequency, it's a decreasing of wavelength, and this ascending order of electromagnetic spectrum is also known as the uh, ascending order of electromagnetic radiation is also known as the electromagnetic spectrum. So here, just see here, your gamma rays, it has the wavelength of 10 to the minus 16 to 10 to the minus 12. X-ray, it is 10 to the minus 12, 10. UV is 10 to the minus 8. And in between UV and IR, we have the visible range. That is from 400 nanometer to 700 nanometer. So we have the visible range that is belongs to your VIBGYOR, VIBGYOR, that is violet, indigo, green, yellow, orange, and red. Sorry, Jyotirmay, please mute yourself. Jyotirmay, Jyotirmay. So students are requested to have patience hearing, and in between, if you have any doubt, you may unmute or ask the question. But otherwise, please do not disturb. Uh, so because in between, if you're getting some disturbances, what happened? The frequency or the flow of teaching is disturbed, and the thing I have just uh, been ready to deliver you will not be effective. Okay, so please bear with me and keep your patience. Thank you. So the visible range, it is from your 400 nanometer to 700 nanometer. It includes your different seven different colors. That is violet, indigo, green, yellow, orange, and red. Okay. So then, according to so
Next bus stop is Phantom. পরবর্তী bus stop Phantom.
yes. So according to Planck's law, uh, in transition of electron from a lower energy level to higher energy level, according to Bohr's theory also, last postulate that when an electron is a transit from ground energy level to higher excited state, higher energy level, then it gains energy. And when it jumps from higher energy to lower energy, it radiates energy. And according to Planck, the transition occurs with the loss or gain of energy, but it is in the form of small packets, also known as quanta. So this quanta of energy for hydrogen atom, it is known as the photon. So photon, it is nothing but the quanta of energy which is associated with the transition of electron in hydrogen. So according to Planck, we have E equal to h nu. This is a very famous equation, like Einstein equation equal to mc square. So like this, the Planck's equation, it is a very popular and well-known one. That is E equal to h nu. If I just simplify the equation, then E.
ସାର୍
Okay,
ସାର୍ ସ୍କ୍ରିନ୍ ମାନେ ପୁରା ଠିକ୍ ସେ ଭିଜିବଲ୍ ହଉନି ମାନେ ପୁରା ଫୁଲ୍ ପେଜ୍ଟା ଆସୁନି ତ
ଆସୁନି ଏବେ
ନାଇଁ
ଆସିଲା
ସାର୍ ହଁ
ଏବେ
ସାର୍ ହଁ ଆସୁଛି ସାର୍
ମୁଁ actually ଜୁମ୍ କରି ଦେଖୁଛି ଯେମିତି ସମସ୍ତଙ୍କୁ ଭିଜିବଲ ହବ। ତ ଯୋଉଟା ଯୋଉଟା
ଆଚ୍ଛା
ଇମ୍ପୋର୍ଟାଣ୍ଟ ମୁଁ ସେଇଟା ହିଁ ତମକୁ ଦେଖୁଛି। ମୁଁ ତମକୁ
ସାର୍
ପିଡିଏଫ ଗ୍ରୁପରେ ସେୟାର କରିଦେବି ହେଲା।
ଆକ୍ଚୁଆଲି ବୁକ୍ ନାହିଁ କି ପି ଡି ଏଫ୍ ତ ନାହିଁ ତ ସେଇଥିପାଇଁ ଆକ୍ଚୁଆଲି ସ୍କ୍ରିନ୍ ସଟ୍ ନେବା ପାଇଁ ଇଜି ହେବ ଭାବିକି
କିଛି ସ୍କ୍ରିନଶଟ ନବା ଦରକାର ନାହିଁ। I have also prepared one PPT PowerPoint presentation for you all, and
ଆଜ୍ଞା
also I have the PDF for your IGNO PDF I have. So
ଓକେ
you don't worry for the material. I will share it with your in your WhatsApp group. Okay.
ଥ୍ୟାଙ୍କ ୟୁ
So
ସାର୍
just listen what I am delivering. Just
ଓକେ
focus on that only.
ଥ୍ୟାଙ୍କ ୟୁ ସାର୍
Regarding the material, regarding everything, I will help you. Don't worry. Okay. So according to Planck's law, we have E equal to h nu, and if I simplify the equation, it becomes E equal to h c by lambda. So nu can be replaced with c by lambda, and as we know, 1 by lambda equal to nu bar, that is wave number. So this equation can also simplify as E equal to hc nu bar. So this same Planck's equation, it is now modified to 3 different equations, that is E equal to S nu, E equal to Hc by lambda, and E equal to Hc nu bar. So these are all some quantum mechanical treatment, we may say, which is coordinates the classical as well as quantum aspect of a material. Then the very famous quantum mechanics is just here, and this quantum mechanics, it is associated with your spectra. And according to Bohr's theory, we have as the Bohr's atomic model, it is applicable to single electron species, and it is rather not applicable, or it is have some limitations of being not applicable to multi electron species. So in your hydrogen spectra, we have six different spectral series, which are known as Lyman series, Balmer series, Bastian series, Bracket series, P-Font series, and Humphrey series. Humphrey series is not written here, so this is also there after P-Font. So in a Lyman series, we have a transition of electron from higher energy level to energy level number 1. So in Balmer series, it is higher energy level to energy level number 2. In Paschen, it is energy level number 3, followed by in bracket it is 4, and in default it is 5. So, and for Humphrey it is also 6. So, in this transition, what happened? We have a series of lines. The first line in Lemon series, let us just see here, I'm zooming it. Just see here in Layman series, the first line is n equal to 2 to n equal to 1. And so the first line of any series, it is known as the alpha line. The second line, that is 3 to 1, it is known as the beta line. The third line, it is known as the gamma line. And fourth line, it is known as the delta line. So we have different lines in different spectral series. So we have alpha, beta, gamma, delta, and so on. And like this in Balmer series, we have from the first line it is from 3 to 2, second line it is 4 to 2, third line it is 5 to 2, and so on. So in different spectral series, we have different lines, and these lines are known as the fine lines. Then we have the that is known as the interaction of radiation and matter. Okay, yes. So when these electromagnetic radiations are interacted with matter, the concept is, or the phenomenon is known as the spectroscopy. So what is spectroscopy? It is the interaction between electromagnetic radiation and matter. It is known as spectroscopy. So when electromagnetic radiations of different wavelengths of frequency interacted with matter, then what happened? There is a transition of electron from different states, different energy states. So on the basis of that, we'll get the different characteristics of that matter. Like in, let us say, in ultraviolet spectroscopy. If I put a sample in ultraviolet spectroscopy, then what happen? I will get I will get the maximum. I I will get the maximum wavelength that can be absorbed in that matter. That means in EV spectroscopy, we will calculate, or we will determine the lambda max of the matter. This is known as lambda max. So in EV spectroscopy, we have four type of transitions. So there's the electronic transition. So there's the EV spectroscopy is also known as the electronic spectroscopy. And in UV spectroscopy, we have the four transitions from sigma to sigma star level, sigma to pi star level, pi to pi star level, and n to pi star level. So sigma to sigma star and n to sigma star, pi to pi star, and n to pi star. So on the basis of different type of electron present, that is, it may have the pi bond, it may have the lone pair of electron. So for lone pair, it is from the level n. If we have the pi bond, then pi to pi transition may possible. And in UV spectroscopy, we use the Woodward-Spitzer rule for the calculation of your lambda mass for a particular organic compound. So depending on the monoannular dyne, heteroannular dyne, these are all the organic aspects. Then we have the same mechanism. Just see here, according to Bohr's theory, we have excitation as well as absorption. So when excitation occurs, the electron gets promoted from low energy level to high energy level. When absorption occurs, your energy electron is excited from low energy level to high energy level, and when your de-excitation or your loss of energy is occurred, then energy of the electron is jumps from high energy level to low energy. So we have the different on the basis of the different energy levels, we have different vibrational levels as well as rotational levels. So we have vibrational spectroscopy as well as rotational. And vibrational spectroscopy, it is nothing but your IR spectroscopy. That is infrared spectroscopy. So we have on the basis of the absorption and emission of electromagnetic radiation in a matter, we have two types of spectra, that is absorption spectra and emission spectra. So in absorption and emission spectra, before that we should know the a law that is very famous law, that is known as the Beer-Lambert's law. Just see here, it is the Beer-Lambert's law. I just put that one before you. Just wait. First, we may discuss the Beer-Lambert's law. This one, this. It's known as Lambert's law. So Beer-Lambert's law, it is a combining law of Lambert's law and Beer-Lambert's law. So the first law, which is formulated uh, in explaining the absorption and transition of electromagnetic radiation in a matter is a Lambert's law. According to this law, which is framed in 1760, according to this law, when a monochromatic light is allowed to pass through an observing medium, then the rate of change of intensity of light with the thickness is directly proportional to the rate that is monochromatic medium, then the direct proportional to path length with the concentration of the medium. That is Beer's formula, only the concentration of the monochromatic matter. dx equal to d gas by d into E. And then lastly, we have to ସେ ଗୋଟେ ଦେଇଦିଅ। Am I audible, students? Okay. Okay. So after years numbers now, we have the different energy levels which accompanied your electronic vibration and rotational levels. So as this molecular atom spectroscopy, it is related to the physical aspect of the matter. Okay. So this is here we have the different vibrational levels. Like in the ground state, we have the V0, V1, V2, and V3. As well in the excited electronic state, we have V0, V1 dash, V2 dash, V3 dash. So when we have the excitation or de-excitation occur, the excitation between 0 to 0, that is from ground state 0 to excited 0, that is E0 to E1, and also it's the de-excitation may occur for your 0 to ground state 4, 0 to ground state 3, 2, and 1. So we have on the basis of these different transitions, we have different spectrum will occur. And prerequisites the interaction of radiation and matter we have. So this depends also depend on the dipole moment of the matter, because we have the because when we have the different dipole moment of different matters, then the interaction between the electromagnetic radiation as well as the matter will be different, and we will get different spectrum. Okay. In the characteristics of the spectrum, so this depends on the three factors, that is the position of absorption maximum. So this is obvious because when your absorption maximum has a different position, we will have different characteristics of the spectrum. Then intensity of the absorption band. So when absorption band has different intensities, then we will have a different spectrum. Then also the width. So here is beautifully we have a spectrum, that is its position, that is exactly at the center, and we have a very uh, that is measurable width as well as the intensity.
It's also considered.
Then under position, the position of the spectral band measured in terms of frequency, wavelength, and wave number in general is identified in terms of lambda max, which is this is determined from a UV spectroscopy, and it corresponds to the wavelength of the maximum absorption in the spectral band. Spectrum may have any number of spectral bands, each with its own lambda max. It is a measure of the difference in the energies of the electronic level involved in the most intense transition in a spectral band, and the electromagnetic spectrum wavelength is inversely proportional to energy, as we already know. So then the intensity part, the intensity of the absorption band depends on three factors. The number one is the population of the energy states. So under population of the energy states, we have the number of atom or molecule that initially in the state from which the transition takes place. Then the transition probability the likelihood of the transition. Then we have the path length, the sample, the number of the species, and the amount of the substance being analyzed. So these are the key factors on which the intensity spectrum depends. Then what is population of the energy state? Population of the energy state. So we have a equation according to Boltzmann statistical distribution. So this is Ni by N naught. It is equal to E to the power minus delta E by K, where Ni and N naught are the population of the ith level and the ground state respectively. Delta E is the difference in the energy to the ground state and the ith state, delta E. And Kp is the Boltzmann constant, which is 1.38 into 10 to the minus 23 joule per Kelvin inverse, and T is the absolute temperature. So, depending on the equation, then we have the population of the United States, which is very much calculated. We have a problem here that is calculate the population of an energy level having energy of 20 kilojoule per mole relative to the energy at ground state at 300 Kelvin. So we have the T given, we have the delta E we will calculate, that is E final minus E initial, which is equal to 20 kilojoule per mole. So 20 kilojoule means make it joule first, 10 to the 3 divided by per mole means it is number of molecule. This is 6.023, which is calculated as 3.32 into minus 20 joule. Then the formula according to Bohr's Boltzmann statistic equation, that the Ni by N not equal to E minus delta E by kt. As if I put all the values, then it becomes 0.00032. So this implies that for every 10 to the 6 species, that is 1 million species at the ground state, there are just 32 species at the level that has energy of 20 kilojoule per mole or relative to it. So this is how the population can be calculated. So we have the transition for probability also, that is how the transition of electron may occur, and which is depends on the population as well as the intensity of the radiation. Uh, the transition probability, we have a measure of the allowedness of a given transition, whether a transition is allowed or not, and if yes, to what extent. It is a quantum mechanical property and is determined by considering the wavelength of the initial and the final energy state involved in the transition, the electronic field of the radiation causing the transition. If the values of the integral happens to be zero, the transition is not allowed or forbidden. If the value of the integral happens to be zero, the difference in energy it becomes zero, that means this transition is not allowed. Further, the magnitude of the value gives the measure of the allowed mass, also the allowedness. If it happens to be unity, the transition is freely allowed. So if it is +1, the transition between two energy level, then it is treated as allowed. So just wait, student. Just. So the transition is depends on, that is a transition probability, that when the delta E equal to 0, that means it is forbidden. If it is plus 1, it is allowed. There is a transition with low transition probability will be less intense than there is a transition of high probability if all the other parameters are equal. To understand the idea of transition probability in a little detail, we need the following. So let's have a uh, interacting species M and two energy level M and M. We consider a transition to take place from the initial state M with energy M and population N when excited state N. So we have a schematic diagram here, that is we have two energy states, that is M and N, where the energy associated with the M energy level it is EM, and energy associated with the N energy level it is En. So when an electron from M to N it is excited, then it is known as the induced absorption. That is here the energy absorbed is in the form of small packets known as quanta according to Planck's theory. And simultaneously, when an electron it is jumps from higher energy level N to lower energy level M, we will also have the energy level, that is sorry, energy of h nu, which is your quanta of energy, that is E equal to h nu. So it is known as the spontaneous emission. So induced absorption followed by spontaneous emission. Then we have the induced emission also, that is from higher energy level En. Simultaneously, many quanta of energy or small packets of energy may lose. So we have the transition from higher energy level to lower energy level, which is known as induced emission. So induced absorption, spontaneous emission, as well as induced or stimulated emission we have. So for induced absorption, we have an electron in M energy level can absorb an energy of Hc nu bar. It becomes your M star. And in spontaneous emission, we have the emission of energy, that is from M star, we will have M plus Hc nu bar. And under your M star Hc nu, that is induced or stimulated emission, we have the spontaneous emission, that is M star plus Hc bar, it will be M plus 2 Hc bar. So we have the nu bar, where the Bmn it is called Einstein coefficient, and the rho nu bar represents the spectral radiation density, which is given by rho nu bar equal to 8 pi Hc nu bar q divided by exponential of Hc nu bar by kt to the power minus 1. We represent the change in population, that is dnn by dt equal to minus nn dnn rho nu bar. So again the dnn it is known as the Einstein coefficient for induced emission and is equal to Bmn. So on the other hand, if I change the population from nn, then dnn by dt equal to minus nn ANM, where ANM is known as the Einstein coefficient for spontaneous emission. So for induced emission it is BNM, and for spontaneous emission it is ANM. And similarly the equation is now just modified, and Suppose we all have the molecule and the radiation, then all the three processes will occur simultaneously, and the stage will once come when the population of the two energy level achieve equilibrium values. There is further change in the population. So we have d and n by dt equal to, for induced absorption, we have nm bmn rho nu bar minus nn bnm rho nu bar, which is equal to your spontaneous emission, minus nn anm, which is associated with your induced emission. So if I simplify the above equation, then we have the above equation, the dnm by dt equal to nm minus nn uh, multiplied by bnn rho nu bar minus nn anm. And we know that from the equilibrium the population nm and nm are related. So nn by nm, we have the equation that is gn by gm exponential d minus w by dt. So further we will uh, simplify the above equation, and at the end we will get the value of anm in terms of bnm, and the transition momentum rnm also can be calculated, which is equal to integration of psi star n mu psi m dt. So if we just calculate the numbers law. So this is a sample. When the P0 intensity of light is passed through a sample, then after absorption of some light, the transmitted light will be P, and your path length it is equal to P. So on the basis of that, we have the Lambert's law. This is already discussed that when a monochromatic light is allowed to pass through an observing medium, then the rate of change of intensity of light with thickness is directly proportional to known as a Beer's law, Beer's Lambert's law. And in your exam, this Beer's no question, because in every spectroscopy part, this Beer's Lambert's law always be there in uh, uh, so we can for long term. This also is a we observe here the PCA between traveling towards frequency apparently higher than it really is. So this incident already it is experienced by the by all, that when a train she don't then it the frequency of the that engine is relatively very high, and then we found then we have the item problem again. Which possible to determine both possible to determine both the position as well momentum of a microscopic particle simultaneously or very accurately. It is impossible for accurate measurement of exact position and momentum of a microscopic particle simultaneously. That if we calculate the calculate your position, then momentum may not be calculated accurately and vice versa. So in Heisenberg uncertainty or Heisenberg, we have minus dn by dt equal to k n n, and this is a Heisenberg equation that del e by del e into del t, it is nearly equal to h cross, which is equal to h by 2 pi. So when Fourier transformation spectroscopy is there, if this spectroscopy is related to your IR, that is Fourier transformation infrared spectroscopy, and this spectroscopy, it is it is a process of continuous variation of wavelength, which is referred to as sweeping the wavelength range. Each point of the spectrum is recorded separately by monitoring and recording the corresponding detector signal. The signals produced by the detector are suitably amplified by electronic means before being recorded. This also includes the undesirable random fluctuations due to electronic signals produced by the radiation source or detector or by the amplifying equipment. These fluctuations are usually referred to as noise. For a meaningful spectrum with a clear signal, the intensity of the spectral peak should be at least 3 to 4 times the background noise. This method of recording is known as your Fourier transform. That is, the information about the signal on the spectrum is collected indirectly in a few seconds in the so-called time domain. The frequency spectrum is obtained in mathematical transformation, which is known as Fourier transformation. And this Fourier transformation technique, it is frequent, it's mainly used in IR spectroscopy. So we have also the free induced decay, that is FID, which is used as the source of the electromagnetic radiation. And this decay process, it is nothing but related to also that is type of source used for a particular spectroscopy. So depending on the type of analysis you are trying to execute, your your spectroscopy can be selected accordingly. Then we have the summary and the transition, and we have some terminal questions are here. Let's go through this. So this is all about the unit one. So so if anyone having any doubt or anything you wish to share related to your unit one, you may ask. Else we will go for the unit two, because we have the 6 units, and these 6 units will be covered in 4 days. So this is a very technical chapters of chemistry. So everything should be uh, learned or should be understood very clearly. And Dilip,
Sir, good evening.
good evening.
Sir, actually, the topic is relating to introduction to spectroscopy. I have a doubt about where do you use this Fourier transformation spectroscopy in your daily life?
Please speak again. I'm not listening properly.
Sir, I wanted to know, sir, in our practical daily life, where, sir,
Hmm.
do you use about this Fourier spectroscopy?
In our daily life.
Yes, sir.
In our daily life, the spectroscopy application is there. That is testing of food, testing of drinking water. All the that is food safety department is there. That is if FSO, one officer is there, food safety officer, which deals with this spectroscopic analysis, that whether the contaminants or the drinking the water is it is applicable for drinking or not. All these things are there in your state pollution control board, as well as central pollution control board. We have the spectroscopic analysis. Okay.
Okay, sir. Okay, thank you, sir. Sir, actually, what is the thing is, I think you are in outside that background sound is coming very roughly, and it is whatever you are teaching, it is very good, but it is not audible properly due to the background sounds.
Okay. Actually, I am in a crowded place now, so I'm trying to go to a lonely place. Okay.
Okay. Okay, sir. Thank you so much, sir.
Welcome. So, thank you, Dilip, for your kind response. Then we will have the second unit that is related to your. Just wait, I'm opening the PDF for you. The unit two. This is the unit two you have, which is related to the atomic spectroscopy. Okay. So related to this, I have a PowerPoint presentation also. Just I am sharing the thing. Just wait. Just wait. I'm just sharing the thing. Yes. So in atomic spectroscopy, we have the spectral analysis in at atomic level. So what is an atom? So it is the smallest particle of an element which may or may not have independent existence. So under atomic spectroscopy, we have atomic absorption spectroscopy and atomic emission spectroscopy. So under atomic absorption spectroscopy, we will able to find out the percentage of different elements present in a particular sample very precisely. And this atomic spectroscopy, I think the PowerPoint presentation is very much visible to you all students.
Yes, sir. Visible.
Okay. So this atomic spectroscopy it is used to determine the concentration of the element in a sample, and it has also played a major role in the development of our current database for mineral nutrient and toxicant in food, which is already asked by Dilip. And these spectroscopic method are used for the qualitative as well as quantitative measurement of more than 70 elements. And this is a very accurate and very precise method, which is very widely used in different advanced research labs, IITs, NITs, and in central universities. This atomic absorption spectroscopy it is very widely used for the estimation of different elements present in different concentration. And typically, this method can detect the element at ppm level, that is parts per million level, 10 to the minus 6, 2 parts per billion also, 10 to the minus 9. And in some cases, it is even smaller. So atomic spectroscopy method are also rapid, convenient, and it is usually of high selectivity. So there are several types of atomic spectroscopy. That is atomic absorption. We'll discuss it in detail. Atomic emission also, that is AES, and inductively coupled plasma. It is known as ICP-MS, inductively coupled plasma mass spectrometry, are some of the examples of our atomic spectroscopy. So, these three instrumental method have largely replaced traditional wet chemistry method for mineral analysis of food, although traditional method for calcium, chloride, iron, and phosphorus remain in today's discussion. Then just see there are a list of elements here which are very much very precisely calculated by atomic spectroscopy. Like the essential nutrients like calcium, phosphorus, sodium, potassium, chlorine, magnesium, iron, iodine, zinc, copper, selenium, chromium, manganese, arsenic, boron, molybdenum, nickel, and silicon. All these essential elements can be determined very precisely, as well as the toxicity of some elements like lead, mercury, cadmium, nickel, arsenic, and thallium. This can be calculated, determined very precisely. As we know that the food company named Maggi, which is manufacturing the noodles, and this Maggi Maggi oil. So this noodle company is 2 years back it is banned due to the percentage of lead which is present in that movie, which is unfair to the human health, and that percentage of lead it is determined by the atomic acoustics spectrum. So here is some elements which are highlighted in the pink color. These are determined at ppm or ppb level at by atomic acoustics spectrum. So A is quantifies the adjustment of electromagnetic radiation by well separating neutron from atom or excited by heat or other means. So atomic spectroscopy is particularly well suited for analytical measurement because atomic spectra consists of discrete lines and every element has an unique spectrum. It is obvious that different elements have different spectra. So therefore, individual element can be identified and quantified accurately and precisely even in the presence of terms of other elements. So we will have the general principle of atomization, how the different atoms gets converted to gaseous atomic state, and how their spectra is determined or predicted. This should be discussed, and just um, uh, put a 5 minutes of break here to have some water or some washroom activity. Okay, then after that we will continue. So till then, keep patience. Thank you. Am I audible, students?
Sir.
Yes,
Okay,
sir.
thank you. Thank you. So now the discussion will continue. So is it visible, Pramodini? Okay. So our atomic spectroscopy, it is of various types. Atomic absorption spectroscopy, atomic
Sir, your voice is not.
spectroscopy, inductively coupled plasma mass spectrometry. All these are included your atomic spectroscopy. So atomic spectroscopy.
Sir, the voice is not audible.
Uh, am I audible, students?
Sir.
Okay. So as it is already discussed that atomic spectroscopy, it involves your method of analyzation or method of analysis at atomic level. So it may be atomic absorption, atomic emission, or ICP-MS, inductively coupled plasma mass spectrometry. So under atomic spectroscopy, we have the principle, that is first one is the atomization. So atomic spectroscopy requires that the atom of an element that is of interest be in the atomic state, and that they be well separated in space. That means the matter should be at elemental level. So in foods, virtually all elements are present as compound or complexes, and therefore must be converted to neutral atom before atomic absorption or emission measurement can be made. So atomization involves separating particle into individual molecule. So under vaporization, and we have the breaking molecule into atoms. It is usually accompanied by exposing the analyte to high temperature, that is in a flame or a plasma. So under high temperature, the complexity or the components which are present as molecule or compound or complex, they can be disintegrated or they can be dissociated to atomic level. So we have the principle that is for the atomization process. So we have the flame or the type of source that converts the molecule or the compound to atomic level. So this is the schematic diagram where we have the solution, that is M. So this is at the bottom, which is M water plus into X minus, that is a very complex ion. and it is now desolvation process occur, which is converted the solution to the solid state, that is MXN, which under vaporization will give the solid to your vapor state, that is MX gas. So then, in application to the flame, now the gaseous compound, it is under atomization process and it converted to atoms, that is M, and which upon excitation will give M star or M plus ion uh, under your atomization process. So this is how your compound or a complex is converted to an atom, and these atoms, that is M plus, it can be very precisely, it is analyzed, and the corresponding relative ppb level can be easily predicted. So now your source, that is method of atomization, which is nothing but it depends on the source you have, and depending on the source, if you have the flame, it has the temperature of approximately 1700 to 3150 degrees centigrade, which is applicable to atomic absorption spectroscopy and atomic emission spectroscopy. And similarly for electrothermal, the temperature is 1200 to 3000 degrees centigrade, and it is for the graphite furnace, and it is also your atomic absorption spectroscopy. Then we have the ICP, inductively coupled plasma, and you have the argon as the gas which is used for that atomization process. Then your temperature can be enhanced to 6000 to 7000 degrees centigrade, and it is primarily used for ICP AES or ICP MS. For ICP AES, it is your inductively coupled plasma atomic emission spectroscopy or inductively coupled plasma mass spectrometry. So let's have the discussion on atomic absorption spectroscopy. So it is an analytical method which is based on absorption of UV or visible radiation by free atom in the gaseous state. So as we know that in atomic spectra, the constituent particles are at the atomic state, and here the absorption of radiation occur, that is primarily ultraviolet radiation or visible radiation. It is relatively a simple method which was most widely used form of atomic spectroscopy. However, it is being gradually replaced by ICP and ICP-MS. So AAS, that is atomic absorption spectroscopy, it is a very simple technique, and due to its low precision, due to its low or we may say due to its restricted application, ICP-MS or ICP-AES, these are the advanced tools or advanced techniques with respect to atomic absorption spectroscopy. So nowadays, ICP-AES or ICP-MS, it is very widely used for analysis of elements at atomic level with very high accuracy and then very precise analysis. And the AES involves two steps. That is the atomization. It is the first step, and second one is the absorption of radiation from a light source by the free atom. So it is very clear that we have the two steps of analysis. One is the atomization of the atom to gaseous state to form the atom, and second one is the absorption of radiation. The sample, either a liquid or a solid, is atomized in either a flame or a graphite furnace. So we have two type of atomization process, by a flame atomization or graphite furnace atomization. Upon the atomization, upon the absorption of UV or visible light, The free atom undergo electronic transition from the ground state to excited state. Two types of atomization, flame and rapid furnace. So we have the technique which is used, basically the principle that a free atom generated in an atomizer can absorb radiation at specific frequency. A quantifies the absorption of ground state atom in the gaseous state. The atom absorb UV or visible light and make transition to higher electronic energy level. The analyte concentration is determined from the amount of absorption. Concentration measurement are usually determined from a working calibration curve. After calibrating the instrument with standard of known concentration, this is a very as usual method of standardization of a tool or a instrument, that before analysis of an unknown sample, we will put a known sample which parameters are already known to us, and this is first analyzed with that instrument to make it standardized, which is known as the calibration. Then atomic absorption spectroscopy is a very common technique for detecting and measuring the concentration of metals in a sample at very low level and with great accuracy. It in comparison with traditional wet chemistry method, measurement with AS are extremely rapid. So the traditional wet chemistry method means traditional chemical analysis, that is qualitative as well as quantitative analysis, where we prepare some solutions, we make we do the titration experiment, we do the qualitative and quantitative method of estimation by precipitation, by your color change reactions are also there. So with respect to these traditional chemical weight analysis, atomic absorption spectroscopy uh, mm, stood very high with respect to this. So principle of flame atomic absorption spectroscopy. So here also the same Beers-Lambert's law applies. That is observance. It is equal to log I0 by I, which is equal to ABC or alpha BC, where your A, it is known as the molar absorptivity, B is the path length, and C is the concentration, and I0 is the initial incident of light, and I is the intensity of radiation of the flame. And here, according to Beers-Lambert's law, you can calculate or you can determine the absorbance as well as the transmittance of radiation in a medium. Then we have the atomic absorption instrumentation. Just here, see, this is the instrumentation. We have a radiation source. We have a radiation source, that is the hollow cathode lamp, which is followed by a atomizer, monochromator, detector, and computer. So there are five main parts, we may say, or main aspect of atomic absorption spectroscopy. We have the source lamp, which produces the flame, or we have the graphite furnace lamp, and followed by the atomizer, which convert the compound or the complex to your atomic level in the gaseous state, where the different elements are converted to their gaseous atomic level, and the concentration is accordingly determined at ppm or ppl level. And nowadays these instruments are becoming very advanced, that within a second, within few seconds, not a second, within few seconds, you can get your report, we may say, and get your data within a very uh, fraction of time. Then this is a very simple your instrumentation diagram. We have the monochromator also, which which makes your polychromatic light to monochromatic light with a single wavelength. So when this type of analysis are done, the incident light should have a single wavelength to make the analysis a standard one or standard for standardization purpose. So we have a link here, and accordingly a computer based diagram of your atomic absorption spectra is there, that with this yellow color hollow cathode lamp we have a just wait. We have a flame atomizer is there, which is just like a burning one, and by which your compound or the complex is converted to atom in the gaseous state, and with the help of that monochromator and with the help of different diffracting gratings we will have the detector. Then sample preparation, this is the utmost important step that is in principle any food may be analyzed with any of the atomic spectra method. In most of the cases it is necessary to ash the food, just burn it and it becomes the ash, and the food to destroy organic matter, and the ash is a suitable solvent prior to analysis. Sample preparation of for atomic absorption spectra involves destruction of organic matter by ashing, followed by dissolution of the ash in an aqueous solvent, usually a dilute acid. Because when your organic compound is there, only carbon and hydrogen predominantly, carbon and hydrogen will be there with different functional groups. So with the presence of these functional groups, whether it is alcohol, aldehyde, ketone, ester, ether, amide, cyanide, thiocyanide, any functional group, then your characteristics inorganic elements will not analyze by your atomic absorption spectra. So proper ashing is very important. It is a very critical to accuracy. Some element may be volatile at temperature used in dry ashing and heating to about 500 degrees centigrade to burn of the organic matter, because in under combustion process, when in presence of oxygen, when an organic compound is burned, um, it is converted to carbon dioxide and water. So very easily the carbon and hydrogen part gets disappeared from your food sample, leaving the inorganic aspect in the ash only. So it requires around 500 degrees centigrade. It is applicable. It is very much uh, it is very much 500 degrees very much useful for converting your organic aspect to carbon dioxide and water. Then your after that it is the volatilization is less of a problem in wet ashing. When some acid is added, your ash becomes wet with your nitric acid or perchloric acid, except for the determination of boron, which is recovered better using dry ashing method. So different inorganic elements have different method of separation, different method of analysis. So we have your for boron, dry acid method is preferred, but for most of the inorganic elements, your wet acid method is preferred. So your result and calibration curves. So according to Beer's law, absorbance is directly related to the concentration. However, a plot of absorbance versus concentration will deviate from linearity when concentration exceeds a certain level. So a plot of absorbance versus concentration showing non-linearity above a certain concentration. So this is how your that is atomic absorption spectroscopy works. That there are two steps. The first step is the atomization step, and the second step is the absorption of either ultraviolet radiation or visible radiation. So on the basis of that, your different elements, the different concentration of the element at a ppb or ppm level is calculated or determined very precisely. So this is the one I have, that is atomic absorption, and let's have another. The same thing is here. Okay, I will share it to your WhatsApp group, so don't worry. And under atomic absorption spectra, we have two different source of excitation, that is flame excitation as well as graphite furnace excitation. So in 1955, Walls published one paper on the basis of this atomic absorption spectra. This is the original 1954 atomic absorption spectrum, atomic absorption spectroscopy instrument, which is formulated by Walls, and it is the instrumentation part, how different wavelength of light, detector, monochromator, atomizers are placed in the. And we have the atomic fluorescence spectroscopy. As we know, fluorescence, it is about your transition of element from higher singlet state to ground singlet state, that is the S1 to S0. The transition is known as the fluorescence. So fluorescence and phosphorescence, it is under your photochemistry part, and this can be easily understood with the help of your Jablonski diagram, which includes your inter system crossing, then your IC is there, that is intercrossing is there from same state, that is singlet to singlet. If it is singlet to triplet, it is intersystem crossing, ISC. Then we have the phosphorescence and fluorescence. So when triplet state to singlet state transition will be there, then it is known as the phosphorescence. When it is singlet to singlet, that is a higher singlet state, higher energy singlet state to ground singlet state, it is your fluorescence. So atomic fluorescence spectra, it is another method of analysis to know the different elemental composition of a compound with the help of fluorescence. So here also your flame and also non-flame. The method of atomization is important. For flame, it is sample solution aspirated into a flame. For non-flame, it is sample solution evaporated and ignited. Okay. Then the radiation, it is both, it is for your sample. Then in the same process, we have a hollow cathode lamp is there, where the same transition or conversion is happen, that is M solid, that the matter in solid state is converted to gaseous state, and the gaseous state, it is now excited, that is M star. And the M star, it is de-excited to your M gas, and the observed light or energy, it is now emitted. Then the type of atomizer, we have the flame, electrochemical, and special atomizer is also there, which involve glow discharge, hydride generation, and cold vapor. So under hydride generation, we have the H minus generation. So H minus is known as hydride. So flame atomizer is also here. So under nebulization, desolvation, and volatilization, we have the three methods. Under nebulization, we have the conversion of the liquid sample to a fine spray. Under dissolution solvation, we have the solid atom are mixed with the gaseous fuel. Under volatilization, we have the solid atoms are converted to a vapor in the flame. So here also we have the atomization process, where your solution of analyte, it is under nebulization, it will convert it to a spray like matter, And under desolvation, it converted to solid or gas aerosol. Aerosol means it is just a mixture of your air and that means your gas and liquid. Then we have the volatilization process where the aerosol is now converted to gaseous molecule, and uh, it is again converted to your excited molecule with gain of energy, that is h nu. So when the gaseous molecule, it is converted to atoms by the process of dissociation, and it is reversible, and the atoms also get excited by gain of energy of small packets in the form of quanta, that is h nu, and also the atoms is now converted to atomic ion, and these are also excited by gain of energy. So by the process of nebulization, desolvation, and volatilization, the compound or the complex matter is converted to atom, or it is changed to the atomic process. Bhubaneswar, master candidate. Then we have the type of flames. We have the fuel, oxidant, the acetylene, air. If it is the fuel, the temperature is 2100 to 2400 degrees centigrade. Then the acetylene and nitrous oxide, N2O, which is also known as the laughing gas. The temperature becomes 2600 to 2800 degrees centigrade. And if it is acetylene and oxygen, it is 3050 to 3150 degrees centigrade. So these are the flame structure, temperature profile, all these are there. I will just share with you. Okay. So how atomic absorption and atomic emission detection limits are here. Just see this table, students. Here silver, the in flame atomic absorption, we have 3 ppm level of detection, whereas in flame AES, we have the 20 ppm limit of your estimation. For calcium, it is 1 and zero point 0.1. For cadmium, it is 1 and 2000. For potassium, it is 2 and 3. For iron, it is 6 and 50. For various different type of ions or atoms, we have different type of uh, or different range of detection limit in your at your ppm level. So determination of iron by AS, electrochemical atomization is also there, where we have some atomized by with the help of that is electrochemical method, so electrothermal method. Okay. Then in the next class we will discuss the atomic emission spectroscopy and also the optical emission spectroscopy. So up to this, if you have any doubt or anything you wish to share or anything you wish to ask, so please unmute and ask, and then we will wind up the session. Students, on you. So Pramodini, Sucheta, Adyasha, Dilip, Swarup Nanda. So these things are very much technical things. Okay, some terminology you must remember that for this spectroscopy, these techniques is there. For atomic absorption, we have two steps: atomization, and we have the absorption of light. Then accordingly, the elemental analysis in the range of ppm or ppb. What is the accuracy factor, and how your atomic absorption and atomic fluorescence spectroscopy applies, and all the things are there. Hollow hydrogen lamps is there. Then we have the flame atomic absorption spectra, then graphite furnace spectra, all these are there. So if you understand the thing, then it is very easily you can write in your examination, as well as the concept becomes very much clear. So, so actually, I am now in Bhubaneswar railway station. In an emergency, I just go to somewhere. So that's why some disturbances are created in the background, as highlighted by Dilip. So it is I also knew that these things are going on, but as the class is pre-scheduled, so I do not wish want to postpone the class unnecessarily. And on the way, I just uh, carry your classes. So if any doubt or anything you wish to share, you just unmute and ask. Yes, we may wind up the session.
Sir,
Who is the
sir ପ୍ରମୋଦିନୀ
Pramodini?
ସାର୍ ଆପଣଙ୍କ ପାଖରେ ଯେଉଁ ମେଟେରିଆଲ ଗୁଡ଼ାକ ଆଭେଲେବୁଲ୍ ଅଛି ସେଟା ଆମ ପାଖକୁ ଟିକେ ସେୟାର କରିଦେଲେ ଭଲ ହୁଅନ୍ତା ଆକ୍ଚୁଆଲି ଆମ ପାଖରେ
ହଁ ମୁଁ
ନାହିଁ।
ସେୟାର ନାଇଁ ନାଇଁ ମୁଁ ସେୟାର କରିଦେବି। ମତେ ତମର କିଛି ଗୋଟେ ହ୍ୱାଟ୍ସଆପ ଗ୍ରୁପ ବୋଧେ ଥିବ ମୁଁ ଭାବୁଛି।
ହଁ ସାର୍ ଅଛି।
ମୁଁ ଜଷ୍ଟ ମୋର କଣ୍ଟାକ୍ଟ ନମ୍ବର ଟା ସେୟାର କରୁଛି। ତମେ ସେ
ଆଚ୍ଛା
କଣ୍ଟାକ୍ଟ ନମ୍ବର ଟା ଜଷ୍ଟ ଆଡ କରିଦବ ଗ୍ରୁପ ରେ, ଦେନ୍ ଆଇ
ହଁ
ୱିଲ୍
ହଁ
share all the PDFs. Okay.
ସାର୍ ସାର୍
Okay. The number is shared.
ସାର୍
So just add this number to your WhatsApp group. Then after the class, I will share all the PDFs. Don't worry. Okay. TBS as well as the PPT also. I will share.
ଥ୍ୟାଙ୍କ ୟୁ
Okay.
ସାର୍ 9903245892
990
9903245892।
45892. Yes. Okay.
ହଁ ଠିକ୍ ଅଛି
So
ଥ୍ୟାଙ୍କ ୟୁ।
if no question is there, so I extend a deep sense of thanks and gratitude to all of you for your patience hearing. And tomorrow we will have the next class on the same time, that is from 6 to 8 on the same platform. So wish you very best, and tomorrow we will meet again. Thank you.
ଥ୍ୟାଙ୍କ ୟୁ ସାର୍
Okay,
ନମସ୍କାର।
thank you, sir, so much for sharing the ideas in spite of many kinds of difficulties and distractions. And actually, the concept is very not difficult. We will tell concept is easy, but this spectroscopy, electronic transitions, we need to understand very clearly and in a better manner. So whatever you presented, thank you so much. And please, sir, share the notes also, as told by Pramodini madam. Thank
Okay,
you, sir.
okay, 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 okay. Thank you, thank you, thank you.
ନମସ୍କାର ସାର୍।